Hey guys, welcome back to another chemistry lesson. This video is about the periodic trend of metallic character, or not. So, we all know what metals and nonmetals are, so let's talk about some of their properties. Alright, first, whereas metals are malleable and ductile, nonmetals are brittle in their solid state. So what that means is malleable is our ability to take a hammer to it and whack it, and it just flattens out like into a sheet. So this is how we get like gold pounded out into sheets or whatever. And then ductile is our ability to draw stuff out into wire. So we take it and kind of pull on it and it makes a wire, right? That is not the case for nonmetals. They are brittle in their solid state. All right, our metals are shiny and lustrous and reflect light, whereas our nonmetals as solids tend to be dull and non-reflective. Our metals conduct heat and electricity really easily, whereas we consider nonmetals to be electrical and thermal insulators because they don't. For metals, most of our oxides are ionic compounds and they are basic, whereas oxides, including nonmetals, tend to be acidic and they are molecular compounds. And then our metals form cations in solution, whereas our nonmetals form anions and polyatomic ions, specifically polyatomic anions. And then finally, our metals will lose electrons in reactions, which means that they get oxidized, and our nonmetals gain electrons in reactions, which means that they are reduced. So, metallic character as a property of an atom or an element is how closely an element's properties match the properties of an ideal metal. So, more malleable, ductile, better conductors, easier to ionize, all of that, right? And then metallic character will actually decrease from left to right across a period. Hopefully that makes sense, because on the left side of the periodic table are your metals, and then on the right side of the periodic tables are your nonmetals, right? And then likewise, our metallic character increases as we go down the column. So as I go from top to bottom, we're becoming more and more metallic. Nonmetals found at the top of the main group elements, right? Metals found at the bottom. Hopefully we know this. We've seen periodic tables, right? So, while we're looking at it on a periodic table, again, metallic character decreases left to right, which hopefully makes sense because our nonmetals are over here. And then metallic character increases as I go from top to bottom. So, metallic character is related to some other periodic trends, right? Metals generally have small first ionization energies, and nonmetals generally have large electron affinities, meaning our, well, except for noble gases. So, meaning quantum mechanics predicts that the metallic character should increase down a column because our valence electrons aren't held as strongly, and should decrease across a period because valence electrons are being held more strongly as we go across. So, it goes along with ionization energy and electron affinity, right? Our alkali metals, atomic radius increases down the column, ionization energy decreases down the column. They have very low ionization energies, which makes them good reducing agents. They are easy to oxidize. They're very reactive. You never find an alkali metal uncombined with something in nature, never, because they're super reactive. They'll react with nonmetals to form salts. They form compounds that are generally soluble in water, so they're found in seawater. Our electron affinity decreases down the column. Our melting point decreases down the column. They're all really low melting points for metals. And their density increases down the column, except for potassium. It's a weirdo. But in general, the increase in mass is greater than the increase in volume. So here we can see the reactivity with water. It gets bigger and bigger as we go down the periodic table from lithium to sodium to potassium. Very explosive in water. We can see the atomic radius increases as we go down the column. We can see the ionization energy decreases, density increases, and melting point decreases to the point where cesium will actually melt in your hand. Don't recommend doing that. You don't want cesium. A lot of cesium is radioactive. I won't say all because I don't know that for sure, but can be radioactive. So let's don't do this and say we did. But there you can see the trend. All right, our halogens on the other side are very not metals. All right, our atomic radius increases down the column. Ionization energy decreases down the column. They have very good electron affinities, so they're good oxidizing agents and are easy to reduce or add electrons to. Very reactive. You're not going to find them uncombined in nature. They'll react with metals to form salts, and their compounds are generally soluble in water, hence they're found in seawater. And our reactivity increases as we go down the column. They'll react with hydrogen to form acids, so binary acids. Their melting point and boiling point increase as we go down the column. So at room temperature, fluorine is a gas, but iodine is a solid, right? The density will generally increase as we go down the column, just like our alkali metals. So we can see that here, right? Chlorine, gas at room temperature. Bromine is a liquid. Iodine is a solid. That's a little hard to see there. But you can see those trends are reflected here as well. So when these two things get together, you get some really aggressive reactions. Alkali metals get oxidized to be their 1+. Halogens are reduced to be 1-. So then we have ionic bonds that attach them together, and we have an exothermic reaction. Right? That reaction that I showed you with water previously, what happens is our alkali metals get oxidized to become their ion, and we split our water into hydrogen gas and an OH ion. What that means is our metals are less dense, they will float. The ions, the sodium ion and the OH from the water, they'll attach together by ionic bonds, and it is exothermic. Well, it's exothermic on the top of the water. So what happens is that the heat that's being released ignites this hydrogen gas. All right, our noble gases, we know that, again, ionization energy decreases down the column. The ionization energy for our noble gases is very, very high, but it decreases down the column per usual. Our atomic radius increases as we go down the column, but our noble gases are very unreactive. They're only found uncombined in nature, and we use them as an inert atmosphere whenever we need a reaction that can't happen in oxygen, for example. We'll do it in a container where all of the oxygen has been removed and replaced with one of these inert gases, and then we'll perform the reaction in there. All right, our melting point and boiling point increase down the column. All of these are gases at room temperature with very low boiling points, and their density increases down the column. So there you go with those trends again in the data.